Well, first I thank the organizers for the honor of speaking in this assembly. What is that?
It is preparation for next talk. You cannot start, then you cannot end.
Thank you, Michael. Okay. Well, I decided to talk about this subject of second law of thermodynamics for several reasons. First of all, to tell the mathematicians that not everything that mathematical physicists do is field theory and statistical mechanics and partial differential equations. Also to emphasize the fact that there's some good old physics around that demands and cries out for a good mathematical treatment. And some of this is pretty old. The oldest being perhaps the second law of thermodynamics. But there are many other questions that have been hanging around for 100 years or 50 years. Maybe they're not fashionable, but they're ripe for good mathematical treatment. Now, the second law is, I know this is going to shock some people, especially some of my colleagues. The second law is perhaps, not perhaps, I think it is the most accurate law in physics outside of the law of conservation of charge. It's so exact and so precise that if any of you discover a little mistake or a slight deviation from this law, not only do you get rich personally, but you solve all the energy crisis of mankind from now until the indefinite future. So it really is fundamental. Some people think it derives from statistical mechanics, and maybe it does, but surely it does, but we're not in any position to do that derivation. So it's a law that exists, and it would be nice to understand it as a thing in itself without asking the question, what is the basis of it? And in fact, it would exist even if we didn't have statistical mechanics, or even if the world were not made up of atoms. We'd still have a law of this kind. And so I'd like to explain to you our view. Our is Jakob Ingwersen and myself, our view of the mathematical underpinnings of this law. Now, I realize that most mathematicians have heard the name. Maybe you don't know what it is. I will explain what it is in physical terms, but before I do that, I thought maybe it's a good idea to put a buzzword on the blackboard. This is not part of the set lecture, but let me put this anyway. The theme, in a certain sense, is the following. Let gamma be a set, and this a relation on gamma. And this relation is, in fact, a pre-order. I will remind you what a pre-order is, in case you've forgotten. It's like a partial order. And I want to know, find conditions on this setup here. Find conditions so that the following is true, so that there's a function from gamma into the positive, well, into the real-valued function, so that x is related to y if and only if s of x is less than or equal to s of y. So when can I parameterize a relation by a function? And if that function exists, it will depend, of course, on some additional hypotheses. If that function exists, I will call it an entropy. I'll give it a name. And I hope that the function is going to be unique, otherwise I'm in trouble. I hope it will be unique up to some trivial changes like multiplication by constant, things like that. So that's some mathematical buzzwords. Let me start with the physics, if I can figure out how to turn this on. So, what?
Pre-order is partial order?
A pre-order is like a partial order, except that you can have x prec y. That's called prec, by the way, in the tech book. It's called prec. X prec y and y prec x without x being equal to y. That's why it's a... x can be less than y, and y can be less than x, but x does not have to be equal to y. There can be equivalence classes. Anyway, so think of partial order. That's fine. All right, here's the classical formulations of the second law of thermodynamics. Now, I'm not going to explain this in detail. There are some famous names associated with Kelvin and Planck here. Planck did a lot of work on the second law of thermodynamics. All the great classical physicists did. And these are the classy formulations that you find in the textbooks. But just notice that they use some words that are not so obvious. What is heat? What is hot? What is cold? What is temperature? I mean, they're sort of implicit in these definitions, but you're supposed to know what those words mean, but you may not know what the words mean unless you, I mean, it's sort of a little bit circular. Carathéodory, who was the mathematician who got into the act and spent a lot of time on this subject, tried to describe the second law, namely this function, this S, in terms of something, in terms of differential forms. And he tried to make it into a problem in local analysis, which he did from a certain point of view, except it's not so easy from his formulation and his theorem, which essentially is based on Frobenius' theorem. It's not so easy from that to get to a global formulation, which is, after all, what you need in the real world. Anyway, these are just some classical words, and if you've seen them before, fine, and if you haven't, well, I would not have the time. The chairman will not allow me to explain all those words. So these are just some things for you to think. What? Oh, yeah. Oh, good. Okay. Thank you for reminding me, because I would have forgotten. Is that okay? Yeah. Okay. Oh, by the way, we wrote up a summary of this in the notices of the AMS if you want to look at it. And also the long paper. This is the first line is the AMS notices. The second line is the physics reports, which is 90 pages, proving all the theorems. By the way, these theorems turn out to be A, numerous, B, tricky, but C, simple, essentially. Simple but tricky. All the theorems are like that. The proofs, I mean. So I will not prove anything. Yes? You shouldn't think about it. Stop. Don't think anymore.
One second. So, I mean, isn't the condition that every two elements should be related?
Yes. No. It's a...
Because S of x is always either smaller than S of y or bigger than S of y if they are really unit numbers. Mm-hmm. Therefore, x and y, every pair of elements... So
you've already realized one condition.
So it must be a total order, right? But that's...
Yes. You've already established one point. Yes. You're okay, good. No, I should have... I should have put, I didn't want to spend time on this. Thank you, Mr. Chairman. What I really meant here was that if x and y are related, then this is true. Right.
So you wrote if and only.
Yes, but because there will be cases where they're not related at all. Okay, so now these are some basic concepts I'm going to have to explain. Thermodynamic systems and copies and things. So let me begin with the bottom here. What I have in mind are a bunch of different kinds of systems. So you should think of a container containing, say, water or hydrogen or whatever, and this container has a piston, so you can change the volume, and it has various states that it can exist in. So here's an example, a mole of hydrogen, and the possible states of this system. This is the state space gamma. So this hydrogen gas can be in various states depending on how much energy is in it and how big the volume is that you've allowed it to be. Usually you parameterize these states by some point in some Rn, for example, in this case R2, energy and volume, but not necessarily so.
R2 because it's one for
energy and one for volume, yeah. Or you don't have to, but that's an example. Now, an interesting example is D, where you have two containers. You have a mole of hydrogen and a half a mole of oxygen. So there's one container sitting here and one container sitting here. And the state space of that is just the Cartesian product of the two state spaces. That is, you describe the state by saying what the hydrogen is doing and what the oxygen is doing. In that case, the state space is some subset of R4. But the parameterization is not important yet. It will be later, but for the moment it's not. Now here you can have a mixture of hydrogen and oxygen. That's quite different. Again, you have one container this time. The state space is, again, R2. Here's an example where you need 3 coordinates to describe it, because I'm going to allow an electric field to be placed on this thing. So in order to describe the state of the system, I have to tell you about the electric field and the volume and the energy. So there are various possibilities. Anyway, you imagine this. You have various systems in the world, and each system has various states available to it. These are equilibrium states. That means if you let it sit there, it will sit and not do anything. It won't explode. It'll just sit. Now, for each state space, we imagine that we have this relation, prec. Now, what does prec mean? Well, prec means that I start the system off in a state X, and I'm allowed to do anything I like to this system, almost anything, except that at the end of the day, after I've finished doing or whatever I'm going to do to the system, I have returned to my initial state, and perhaps a weight got lowered, and otherwise the system has changed. So let's put it another way. I take this container of hydrogen with a piston. I open the door to that room. I put the container in the room. Behind the door is a gorilla. Okay? Now this gorilla, it's like, some of you may remember, there was an advertisement for luggage. Remember, you take your suitcase to the airport counter, you give it to the young lady, she puts it behind the door. Behind the door, there's a gorilla who's jumping up and down on this thing. And at the end, you get the luggage back in some other state. Well, same thing. So I take this container, I put it in the room, the gorilla jumps up and down, does anything he wants, how arbitrarily violent. They can tear it apart. But at the end of the day, I open the door, and I observe that the gorilla is back in its original state. The gorilla is a metaphor for the universe. And the system might have changed. It's now in another state. It's back in equilibrium, but maybe another state. And maybe the only other thing that could change was there was a weight in the room, and the weight might have gone up or down. A weight. An ordinary weight, a stone. That's the only thing that could have changed other than the system. In the meantime, what was going on behind that door is arbitrarily violent. And if I start with X and I can end up with Y, then I write X prec Y. And I keep a list of all these possible things. I make a big list in a book of all the possible initial X's and all the possible final Y's. So there are a bunch of pairs. And this is going to be...
There is no radiation from the outside of the world. Yeah, you mentioned radiation could be there. Because if you radiate something, it goes away, but you remember it happened.
Yeah. So nothing happened in the end to the rest of the universe except that a weight changed. Now, let me just use the notation with a double prec to mean that I can go from X to Y, but not from Y to X. If I can go in both directions, then I write X is equivalent to Y, and I put a little A on top of that. A stands for the word adiabatic.
Anything you do, temperature you change the radiation, how it can come back.
Yeah, forget the radiation. Yeah, so there's reflecting walls in the room, whatever. Okay. Now, not every pair x and y exists in this table. And if either x is prec y or y prec x, then we say that they're comparable. So it's not true that for every pair you can go one way or the other way. Sometimes you can and sometimes you cannot. And those that you can do, you say, are comparable. Okay, now, the entropy principle, which is the metaphor for the second law, is that there's a function on the state space of every system. So the hydrogen container, the oxygen container, each one has a function on it, on the function of all the states of that container, which satisfies first monotonicity. That's what I wrote on the board over there, that I can go from x to y if and only if s of x is less than or equal to s of y. If they're comparable. I mean, if they're related. Otherwise, I don't say anything. Okay? Additivity. Now, this is the crucial thing, because without this, the answer is very ambiguous. But with this thing, it becomes nailed down. If I take the Cartesian product of two systems, so container of hydrogen, container of oxygen, let's say, and I make the product space in the obvious way, then that's a system, because I could put that in the room with the gorilla. So it's supposed to have an entropy function. It's now a function of two variables. And I demand that that function of two variables be the sum of the functions for the individual systems. So I demand additivity.
I suppose 2% comparable if each 2% comparable if each code.
No, within one system, they're comparable if I can go from x to y or y to x. That has nothing to do with Cartesian product. Cartesian product is something else. It just means I have a system with twice as many degrees of freedom, or twice as many variables.
What is the order?
Oh, sorry, what?
What is the order?
Well, there is going to be some ordering on that system, and I want the ordering, I want everything to fit together. I want the ordering to be such, I would, on this second system, on this Cartesian product, there is, of course, a prec, because trivially, there's I can go from x to y or x prime to y prime. That's certainly something that the pair can do, but the pair may be able to do more things. So there is some function, I hope. I haven't derived it yet. I'm trying to derive one. There is a function, and I hope that the function on the Cartesian product, I hope, will respect this condition. This is what I would like to happen. I'm not saying it's automatic. I'm saying I would like it to happen. And if it does, then I'm going to call the function s, which is now going to be given for all possible systems. Each system will have an s. And the s for Cartesian products will be the sum of the s's for the individual pieces. That's what I would like to happen. And if it does happen, I'm really going to call that an entropy function. And I'm going to say that's the second law, the existence of this function. And what is really, really, really remarkable about this, I mean, you look at it and you say, well, that's mathematics. But what it tells you is something absolutely extraordinary, because it says, if you think about it, it says that in the Cartesian product, first of all, there are obvious pairs y, y prime that I can get to from x, x prime. Namely, if I can get from x to y and x prime to y prime, then obviously I can get from the pair. So that's going to be trivial. What is not trivial is that this equation tells you the new things that can happen. You see, I can go from x, x prime to y, y prime. The entropy of the first one could go down. The entropy of the second one could go up. But the sum has to go up. And that tells me precisely what the new possibilities are that are not obvious.
So you can have several ways, not one way, but several ways.
No, what do you mean by ways? Just that you can go from x prime to y prime by some means or other. I don't care.
Yeah, by the process, and then someone changes different position of several ways. Yeah.
What do you mean by ways?
One store on one, containing another store, another containing. It's also a by the process.
Yes, sure.
Several ways, but one way, but several ways.
Several ways of what?
No, because your definition of order depends on only one way it has changed. Right?
Oh, weight.
Weight.
Oh, I'm sorry. I thought you said ways. Yes, of course.
Many ways.
Of course. Well, actually, many weights is the same as one weight because you can combine them. You can tie them together, so that doesn't change. Yeah, if it makes you happy, use as many weights as you like. Now, the next thing I need is a notion of scaled copies that I have to imagine that not only do I have this container of hydrogen with a mole in it, but I also have a container of half a mole of hydrogen and a quarter of a mole and 2 moles and so on, and that they all behave exactly the same way. So I have scaled copies. In other words, for every state space gamma, I'll write it over here in the corner, for every gamma I have lambda gamma, where lambda is a real number, and the obvious things happen, and I demand that the entropy behaves linearly, homogeneously. Huh? Sorry. No, I mean gamma. I'm sorry. I'm writing on top of myself. For every state space gamma, there's another space lambda gamma, where the points of this space are written as lambda x. If I'm parameterizing these things by points in some Rn, then lambda means what you think it means. And the entropy should behave linearly under this scaling. Okay, so if that function exists, then I say I have the second law of thermodynamics. The second law of thermodynamics is the existence of this function that tells you exactly what can happen and what cannot happen. So, question is, which properties of this relation ensure the existence and essential uniqueness of this function? Can we derive this from some simple physical principles? And then there's questions of convexity. That is, if I parameterize things, the state space of a system by a point in some Rn, then I want the entropy function, which is now a function of real variables, I want it to be a concave function. Now, this fact was understood by Gibbs and Boltzmann and everybody because it ensures thermodynamic stability. But let me not go into that. Anyway, this is well known. And now, what about temperature? I haven't mentioned temperature at all. Hot and cold, it hasn't been discussed at all. What does temperature have to do with any of this? Where does that come in? Well, that will come in at the end of the story. That will be the very last view graph, if I get to the last view graph, because the temperature and the notion of hot and cold ought to be and is a derived quantity, and it will turn out to be a partial derivative of the entropy function once I get it and once I learn how to parameterize state spaces by subsets of some Rn. Then the entropy will be not only a function on this subset of some Rn, but it will turn out to be a differentiable function, and it will turn out to be a concave function, and hence differentiable almost everywhere, and that derivative will, with respect to one of the coordinates, namely the energy coordinate, will be called the temperature. But that comes later. So temperature is a derived thing. Now, the conditions on this relation, well, what do we need? Let me not go through this in detail because it's not so much time, but it's the obvious things: reflexivity, transitivity, consistency on the Cartesian product. That is, if I can go from x to x prime, and if I can go from y to y prime, then I can go from the pair xy to x prime y prime. Huh?
Abstract sets. What's scaling with?
What is what?
Form. The abstract sets. How do you define scaling? The abstract.
Well, abstractly, this is just a mnemonic. Abstractly, there's for every real number, there's a set, space. And the space consists of points which are mnemonically written this way. For the moment, that won't mean anything until I come to here. This is what it means. That is to say, an adiabatic, an equivalence, adiabatic in both directions, is that I can take a system with a state space and a point x, a state in the system, and split it. I can take my hydrogen container with 1 mole and split it into 2 hydrogen containers, one with 1 minus lambda moles and the other with lambda moles, and with the same state, if you like, so to speak, except it's 1 minus lambda times it and lambda times it, and I can go back and forward. So there is this relation which extends from a state to Cartesian products. Now, there's no topology at this point, but I'm going to need some notion of continuity, even though there's no topology. So how do we do that? Well, the way we do it is we say, suppose that I can go from x and a little bit of something else, a grain of dust, from a state x and some system and a little bit of grain of dust of something else, to a state y in the same system and a tiny little bit of grain of dust. Suppose I can do that. And suppose I can do that for an arbitrarily small grain of dust. Then the assumption is, the axiom is, that I could have done it without the grain of dust. So that's a notion of continuity without topology, by looking at Cartesian product. Now, that implies, it turns out, the cancellation law, which is written here, that if I can go from x and z to y and z, for any fixed z, then I can go from x to y directly. That's a theorem. That's the first theorem, if you like. Now, I'm going to go through this rather quickly because this whole thing, because there is not so much time. But now I'm going to make a hypothesis that this list of pairs x and y, and also the list for the Cartesian product, this list is sufficiently dense. If the list is not dense, that is, if it's very thin, if only a few points are related to each other, then it may not be possible to fulfill what it is I would like to fulfill. You can easily cook up counterexamples where there is no function that will describe the pre-order. It's not hard to do. You can do it with 5 points. But what I'm going to assume is that if I take a system and take a Cartesian product of it with itself, but all possible scaled copies, then if I take any state in the Cartesian product and any other state in the same Cartesian product, they're comparable. That is, I can either go one way or I can go the other way. That's what comparable means. So you need some hypothesis. Again, I repeat myself, but you need some hypothesis that says the list of pairs, the points that are related, is thick, heavy, dense, whatever. I'm using these words poetically.
If we take lambda equal 1, doesn't this just say that all the states are common?
Yes, in the same state space. Yes, that's exactly right. It says that in particular. It says a lot of things.
Same state.
So in other words, all the states in gamma, inside gamma, are related. So here's my container of hydrogen gas. Take any 2 states, that is defined by an energy and a volume, if you like. Any 2 states. The gorilla can get me from either from one to the other or the other way around. The gorilla is that clever. For any 2 states, which is true. If I take any 2 states of a container of hydrogen, I can get from one to the other.
So what can be What can be uncontrollable?
Well, yeah, I can take a state consisting of, well, whatever. Actually, there are quite a few things, but essentially, the things that are not comparable. Later, by the way, sorry, let me backtrack a little bit. I did not exclude the possibility that some of the things that the gorilla can do is change one system into another. That's also possible. For example, I didn't exclude that. For example, I can have a container of whiskey and a container of water, and the gorilla can mix the whiskey in the water. So that's a third system. That's possible. So there are going to be adiabatic processes that take one state space into another. That happens all the time. And many of these pairs are not comparable. And in fact, what we believe happens, in the real world is all states with the same chemical composition are comparable. That's what we believe, but this is not essential. Right?
So what is gamma?
Gamma is the state space of some system, which itself could be a product of things.
So this correlation is given.
I should erase this because this was only meant to get your mind going, but you shouldn't dwell on it too much. Because if you start thinking about this, you'll get confused. So do you mind if I... yeah. So now we're back to the standard catechism. Okay. So now, let me repeat this because it's very important. It was realized about 1945, 1950, and so on, by several people that what was really essential to get the second law going is that the second law is something that tells you which processes are possible and which are not. And what was really necessary to get this going in a consistent way and describable by an entropy function is that there have to be a lot of processes. If you only have a few, then maybe it is possible to have a situation in which there's no entropy function at all. It's necessary to have many. So the assumption we're making, and the assumption everybody else who looked at this makes, is that there are not only a lot of processes, but everything essentially is possible within one given state space. And that seems to be true physically. Not seems to be, it is true as far as we know. And so we're going to assume that. Now, it turns out that if you make all these assumptions, then the following is true. This is the sort of first main theorem that comes out of this. I hope you will understand that I'm trying to be a little bit poetic here and being very rough and not terribly precise, because if I start being very precise, this lecture will last forever. So it turns out the following is true. If you take a whole bunch of containers, state space 1 with lambda 1 moles in the state x1, lambda 2 moles of the second system, a different system, or the same, it doesn't matter, in the state x2, and so on, that I can get from that to maybe different numbers of moles of different numbers of things, if and only if, there is a function s so that this is true, that I can get from here to here if and only if the sum of the lambdas times the entropies is less than or equal to the sum of the lambda primes times the entropy. That's equivalent. That statement is equivalent to the conditions that I wrote down before on the previous view graph. So it takes a while to prove this, but those conditions establish the existence of a function. And that function, one for each state space, that function on each gamma is, I'm sorry, at this point it's only a single system, sorry, but it's going to be true for an arbitrary number of systems. The entropy function is unique up to an affine transformation, that is by multiplication by a constant or by addition of a constant. So up to an affine shift, which is a shift of scale, the function is unique. And what makes it unique is this assumption of additivity.
How many additive constants when you add things together?
How what?
Additive constants should disappear, no? Because we have additivity.
Yes, the constants disappear. So that's, yeah, the additive constants. But they're going to come up later. They won't disappear forever. The reason they won't disappear forever is I can talk about adiabatic processes which involve mixing. I'm jumping now to the end of the lecture. But with this whiskey and water example, if I have an additive constant for the whiskey, which I don't see as long as I leave the whiskey alone, and an additive constant for the water. And I mix the two together in one container, which is, you know, whiskey on the rocks or what have you. No, it really isn't, but you know, let's say whiskey and ice, so it's solid water. And I make whiskey on the rocks. This is one container made out of two. Then the additive constant comes in. And the determination of that additive constant is tough. It's difficult. All right. Now, I just lost my U-graph. Did it? It was just here a second ago. Did I drop something? No. The gorilla. Yeah. Ah, here it is. Yeah, it is on there. Oh, okay. Now, how do you define this function? Well, it's defined in the following way. It turns out, you take two fixed points, fiducial points in the system, any two that you like, so that they're not equivalent. And you then ask for, you take an arbitrary point x, state x, and you ask what is the maximum amount of stuff in the higher entropy, or yet to be defined higher entropy state x1 that I can use, bring down to x by the use of a lower entropy state x0. And the maximum lambda that I can do, achieve this with, is called the entropy of x. And that has all the right properties. That's the basic definition. It's like the following. If I wanted to find the temperature of something, one way to define it is ask how much ice can I melt with this object. And what?
Is it not comparable? Why?
They have to be comparable because I made the assumption that within a state space, or within pairs of state spaces, all points are comparable. That was one of my assumptions. So that's consistent.
It's actually, you use the theorem here, not the assumption, right? Because you have 1 minus lambda and lambda.
Well, the theorem is, and the construction go together.
This is for the proof. It's obvious for the proof.
So you have to prove that this construction works. And then defines a function, and that function is going to have all these properties. Okay, now let me skip over some stuff.
This function is essentially dependent of the choice of x0.
Yes, this up to an affine transformation, that function is independent of the fiducial points that I started with. Exactly right. Okay. Now, I have to move forward. So far I've been rather general, and I've assumed this comparison hypothesis that you can go from any pair of states essentially to any other pair. But I have to prove that somehow, or rather I would have to make it plausible. And in order to make it plausible, we introduce the simple systems, actually the systems that I've been talking about up to now. But up to now, the systems have been, I haven't stated explicitly what they are, but now I'm going to be very explicit. And talk about simple systems, which will be the basic building blocks of all possible systems by taking Cartesian products. So a simple system is described, now we get down into the dirt and start doing some work. It's defined by, first of all, that it's describable, the states are describable by some convex subset of some Rn, actually Rn plus 1. And there's one very special coordinate called the energy. Now the fact that you can use the energy as a coordinate to describe the state of a system is basically or essentially the first law of thermodynamics. The fact that the energy is a good coordinate is the first law of thermodynamics. In other words, if I tell you that I start from a point x and I get to some other point y, by the gorilla, the amount by which the weight went up or down is independent of what the gorilla did.
Do you assume that there is a minimum of entropy in the system?
No.
No, you don't.
No. So once again, the fact that energy is a good coordinate, that is the height of the weight, is the first law of thermodynamics. That's conservation of energy. So there's this very special coordinate, and I have to make some assumptions. Let me not go through that because I don't have the time, but I'll put it here in case you want to read it. And what comes out of that is the following. I'm going to assume that at every point in this state space, in this convex set, the forward sector of a point, that is the points I can reach by the gorilla, has a unique support plane. And that is the set that I can reach is convex, and it has a unique support plane. And the coordinates of the support plane I'm going to call the pressure. And I'm going to assume, this is the one analytic assumption in the whole game, that this pressure function, which is now a function of where I am in the state space, is Lipschitz. There's another assumption about connectedness of the boundary. Well, that's unimportant. But the real thing is that the pressure is Lipschitz. And if you play with that for long enough, you come up with, and use the usual Banach fixed point theorem to solve the differential equation, you come up with the following picture, that what the equivalence classes, that is the states in the state space that you can go between in both directions, these equivalence classes are convex surfaces that foliate the convex set, which is the state space. So this is an analytic theorem. It's the only analytic theorem in the game, but what it does is establish the comparison. That is, if I take any 2 points, I can either go from here to here or backwards. That is, one is in the forward sector of the other, or vice versa. That's what comes out of this. So these are all points with the same entropy. And
V is volume. What is
V is all the other coordinates, which I'm symbolically writing as V. These are the so-called work coordinates. Volume is a typical one. Magnetization that Tom Spencer was talking about is another one. Electric polarization is another one, and so on. But typically, it's just volume. So this is what comes out. This is what the state space of a simple system looks like from the point of view of thermodynamics. And now I have the following problem. So we have a given state space, say hydrogen. It's a point. It's a simple system. A point in the state space is described by an energy. That's a good coordinate. Not temperature, not pressure, energy. Because that's the weight that the energy and the volume.
the so-called extensive coordinates?
Extensive coordinates, exactly. But it's not, they are extensive, but they're also more fundamental than that. I mean, in the sense that energy is there because of the first law. All right. And I can define an entropy function, and then if I take, I defined it for you, and then if I take Cartesian products of several containers of hydrogen, the entropy function is additive over the taking Cartesian products, and everybody's happy. But now what happens if I try to compare the entropy of hydrogen with the entropy of oxygen? So now we have the following very interesting question. Here's a container of hydrogen and a container of oxygen. If they don't interact, everything's fine. They just do their own thing. But now suppose the gorilla is going to take these two containers, smash them on the floor, let them stir up, later on reassemble them into two containers again of hydrogen and oxygen. The weight has gone up. The gorilla has gone back to its original condition. And I would like to know that the states that I can reach, the pairs of states that I can reach, are given by the sums of the two entropy functions. But the two systems have nothing to do with each other. So how do I compare the entropy functions? I have to be able to compare them if I'm going to add them. For example, if I take one of them and multiply by 36, it will still be an entropy function for the first one. But obviously 36 times something is not the same as 1 times something. So if I'm going to add two things, I have to know how to compare them. That's where the zeroth law of thermodynamics comes in. This is a somewhat complicated story, and I've written this down, but now I realize it's going to take too long to explain. But the basic idea is, if I take two systems, any two systems, and fix the work coordinates, that is, fix the volumes, and specify the total energy, two simple systems now, and specify the total energy, there's a way to break up the total energy into the, put it into the two systems so that the sum is preserved. And in such a way that I have now two states for these two systems, so that any other pair of states with the same total energy and the same individual work coordinates can reach that state. That state lies above any other pair with the same total energy. So that means I have a new system described by twice as many work coordinates, but only one energy, namely the sum of the two. And the assumption is that this new combined system, which you should think of as the two systems with a little copper thread between them, so that heat, quote unquote, which nobody has ever seen, so that heat can pass between the two. That system behaves like a simple system. It's got one energy coordinate and several work coordinates. And the zeroth law of thermodynamics is that the transitivity of this relation. That is, if I take x and y, two state spaces, and I specify the total energy, and now they're nicely in equilibrium. That is to say, the energy is split up in the optimal way. I take this one, and they're split up in the optimal way. If this guy is the same in the two cases, then that and that guy are in the optimal relation. That's the zeroth law of thermodynamics.
So, but it changed dimension. It was...
Yes, right. But this notion of thermal equivalence says that when I split up energy, given the total energy, there's a way to split it up. If the split up here is consistent with the split up here, then those two are in equilibrium. With whatever work coordinates, for every work coordinate here and every work coordinate here, there's a way to split up every energy. And if these are okay and these are okay, then those two are okay. That's the zeroth law of thermodynamics, and it's that property that relates one system to another. So that has to be brought in, and this is now a complicated story, and I don't have time to do it. But
you can first define the temperature as the derivative of energy.
no, we haven't got there yet.
You don't?
All I know is I haven't defined temperature. I just defined this notion of splitting up energy. That's all. I haven't talked about temperature, and I haven't said one is hot or cold or anything of the kind. All right. Now, I'm obviously running out of time, but let me do what the chairman said and define the temperature. But I will now do it, and then we can stop. Then you'll be happy. Okay. So, for every system, we have an entropy. The entropies are consistent because of the zeroth law of thermodynamics. Now, you remember I said that the simple systems had one very important analytic property, namely that these curves of constant entropy, these guys, which foliated the state space of a simple system, they look like that. They really foliated that way. And it turns out that the entropy function, which is defined in the way I did it on page 5, way back, ends up, because of the Lipschitz continuity of this pressure function, ends up being differentiable. It just comes out that way. That's a theorem. It's not an assumption, it's a theorem. And since the splitting up of energy between two states maximizes entropy. Remember I said splitting the energy you split, given a total energy, you split it in such a way that any pair of states with the same total energy can come to that given pair of states. That means that that given pair of states has to have maximum total entropy. So maximum total entropy means by calculus 101 that the sum of that the derivatives have to be equal if the functions are differentiable. But since they are differentiable, that's a theorem, then you find that the derivative of the entropy with respect to the energy is a number. And that number, which I'm calling 1 over t, is a constant work order. That number is the number that characterizes when you're in thermal equilibrium. That is when the zeroth law tells you how to split things up. You split it up in such a way that the derivatives are equal, which is the same thing as saying that these numbers t are equal. So temperature comes out at the end of the story as a derived concept, which is where it should be. It should not be at the beginning of the story, which is where it normally is. It really should be at the end, and that's the end of my story too. So thank you very much.
Thank you.
Huh? By the way, if you want to read about this, I'm very happy to see this enthusiasm. Then you can look at these here. You can look at these articles. What?
Till next talk.
Leave it till next talk. Okay. All right. Good.
All right.
So we have a break.
So